Hello, today we're going to talk about structure 3.2.1 and 3.2.2, which is a nice introduction to organic chemistry. We'll go over the different types of formulas, how we represent organic molecules, and we'll talk about the different functional groups that are important for organic chemistry. Okay, so let's take a minute to review empirical and molecular formulas. The empirical formula is the lowest whole number ratio. We can find an empirical formula using percent by mass data. So let's say, for example, I have a compound that's 85.7% carbon by mass and 14.3% hydrogen by mass. What you can do to find the empirical formula is pretend the percents are grams. That would be if you're assuming it's a 100-gram sample. Then convert grams to moles using the molar mass. I'm just simplifying here to make it go quickly. So when you do the 85.7, that would be 7.14 moles for carbon and 14.3 moles for hydrogen. Then to find the ratio, you're going to divide both by the smallest one. So you'll get 1 carbon for every 2 hydrogen. That means your empirical formula would be CH2, lowest ratio. Now, in reality, you're never going to see a compound that is just CH2 because carbon needs to have 4 bonds to have its octet filled. So that's where molecular formulas come in. Molecular formulas show the actual number and type of elements in a particular compound. Sometimes you'll be asked to find the molecular formula given the empirical formula and the molar mass. So let's say we have a molecular formula that has a molar mass of 70 grams per mole. What you'll do is add up the mass of your empirical formula, which is 14 grams per mole. And we want to find out how many times bigger it needs to be to add up to the 70 grams per mole. So you can just divide. And when you divide there, you get 5. So our compound is actually 5 times bigger than the empirical formula, or C5H10. And so that is our molecular formula. Okay, so now that we have talked about empirical and molecular, let's go ahead and look at structural versus condensed structural formulas. I'm going to use that same C5H10 that we talked about on the last slide. So let's say, for example, if we want to draw out the full structural formula for this, I'm just going to make one up for this one. So let's say it's like this. All right, so there's our 5 carbons and 10 hydrogens. Now, if you just had the molecular formula, you would not be able to determine the exact structural formula unless you had more information. The molecular formula only tells you the number and type of elements in the compound. It does not give you enough information. Structural is going to draw every single bond out. And then kind of a happy medium between the two is what we call a condensed structural formula. So what that's going to do is essentially put all of the hydrogens next to the carbon it's bound to. Or if there's other elements, same idea. It's going to put it next to the carbons that it's attached to. So in this case, we're going to do the 3 hydrogens on this carbon. There's 1 hydrogen on the next carbon, 1 hydrogen on the next carbon, 2 hydrogens on the next carbon, and 3 hydrogens on the last carbon. So that is a condensed structural formula for this one. So it gives us enough information that we could draw all the bonds if we wanted to. Now you can even abbreviate this a little bit further. You could say CH3, CH2, because this repeats. CH2, CH3. So be careful with that. You might also see another example. Let me draw out another example. I have something like this, and I have all of the hydrogens, squeeze it in. So this one is my full structural formula. And I have a whole extra carbon sticking out in the center there. So when I go to draw the condensed formula, CH3, CH2, CH, but I also have this CH3 group sticking off. So I'm going to do like that in parentheses to show that a CH3 group is attached to that carbon. And then I'll keep going CH2, CH3. And so that is a condensed structural formula for this branched hydrocarbon. Now the last two types of formulas are called stereochemical and then skeletal formulas. So stereochemical, it's not very often that you have to draw these, but once in a while you'll see them, and occasionally you might have to draw one. It shows the three-dimensional structure. So let's say I have a carbon in the center, and it is attached to, let's do a hydrogen, and let's say it's attached to a bromine, okay? But remember that carbon forms 4 bonds, and so it will typically have a tetrahedral structure around the carbon. So in order for us to depict that in 2 dimensions, we're going to use a wedge coming out of the page. So this wedge represents that it's like coming towards you out of your screen. Right, let's say that's a chlorine. To show going behind the page, we use dashes like this. And so, I don't know, let's say that's iodine, right? So that would be a stereochemical structure for this compound, showing you specifically in 3D space where the elements are. And again, imagine all 3 of these are in the plane of the paper. So those are all flat on your paper. The dash goes behind, and the chlorine, the wedge for the chlorine there comes out of the paper. The other type of formula that you will probably see is called a skeletal formula. And so let me draw an example. I'm going to do butane here. Remember, carbon needs to have 4 bonds. So there's butane. And to draw a skeletal equation, you just use lines. So if I were to draw a single line like this, the end of each line represents a carbon atom. So it's 1, 2. Now I have 3 carbons, 4 carbons. And you just have to assume that the hydrogens are there. So anytime the carbon needs more bonds, you assume that the hydrogens will fill it in. And so this is the whole structure. Let me draw another one. If I've got like this, that would be equivalent to the carbon in the center, a carbon at the top, carbon on both sides here. Oops. But now we have to fill in the hydrogens. Carbon has to have 4 bonds. So there's 1 more for the central atom, and each of the outer carbons have 3 more hydrogens, like that. So you can see how just using these skeletal drawings save a lot of time for hydrocarbons, so you don't have to draw every single hydrogen atom. And if you have another atom that's not carbon or hydrogen, you will just show that. So let's say, for example, I have, let's do a really simple carboxylic acid. I'll go ahead and draw it all out. Okay, so that's acetic acid. So you can draw that with a line to represent your 2 carbons on either end of the line. Then you can show there's a double bond O, another O, and we usually just put the H next to it. And that is a way to draw acetic acid. A lot of times we won't draw the lone pairs when we're drawing these. And typically if there's a hydrogen as part of a functional group, which we're going to get to in this video, we will include that in the structure, but any other hydrogens would not be included in the structure. So that's skeletal formula. Okay, so I mentioned functional groups a little bit on the last slide. I just want to define that for you guys. Functional groups are specific patterns of bonding in organic compounds that react in a particular way. So it could be a multiple bond situation. So if the carbons have, single, double, or triple bonds, that's going to react in a particular way. If you have like oxygens attached in different ways to the carbon, maybe it's a double bond oxygen, maybe it's between two other carbons. You could even have nitrogens attached. But no matter what, when this pattern of other atoms or pattern of bonding is in your organic compound, it's going to react in a particular manner. And so by defining the functional group, it helps us to classify the type of reaction that it's going to have. Now there's three main types of hydrocarbons. We call them alkanes, alkenes, and alkynes. Alkanes have only single bonds between the carbons, only single bonds. If there's at least one double bond, we call it an alkene, and if there's at least one triple bond, it's an alkyne. For IB chemistry, you're really only going to deal with one double bond or one triple bond for this level of chemistry. Now, this also relates to something called saturation. If you have all single bonds, that means every other position must be filled in with hydrogen atoms. And so we say that it is saturated with hydrogens. It is filled. So if it's only single bonds, it is a saturated compound. Alkenes and alkynes are unsaturated. Because they don't have as many hydrogens as they could have. You could break the double bond or the triple bond and fill in extra hydrogens. As it stands right now, the double bond carbons, you'd need 2 more hydrogens. The triple bonds only need 1 more hydrogen each. So those are unsaturated. Now, this is where you get the terminology saturated fats and unsaturated fats, because they're referring to whether they're only single bonds in the fatty acid structure or if there's double bonds in the fatty acid structure. Okay, so now we're getting into our functional groups. Alcohols. Alcohols have a carbon attached to an OH group. Typically, we will just write OH. In reality, it's going to, have this bent structure. And I will leave that off, though. We typically just draw it like this. Their names end in "ol" for the most part. So if you hear like ethanol, that's the alcohol. The actual group, the OH group, is called a hydroxyl group. So alcohol is the class of the whole compound, but the group itself is called a hydroxyl functional group. The next functional group is ethers. So ethers have an oxygen in between carbons. And so the whole compound is called an ether. Ethers have oxy in the middle of their names. The functional group itself, this part, is called an alkoxy. But the whole compound would be called an ether when it has that alkoxy functional group. Aldehydes have a C double bond O and an H, and it's attached to some other carbon. This is always going to be kind of at the end of a chain or the end of a branch in your hydrocarbon. And the actual functional group part is this part here. And the functional group is called the carbonyl or carbonyl functional group. But the whole thing is considered an aldehyde. Now, I do want to point out that in condensed structural formulas, you will see CHO to represent an aldehyde. That's to distinguish it from an alcohol, which would be a COH. The OH would tell us that the H is on the O instead. Here the H is on the carbon. So just be careful, and I would say it's really worth your time knowing that this represents an aldehyde. It's quick and easy to know that that's the functional group that you're dealing with. Now ketones also have the carbonyl functional group. They have that C double bond O functional group. Label it carbonyl. And the difference is that there's going to be carbons attached to the central carbon. They will both be carbons. So ketones are kind of in the middle of a chain. And you'll typically see in a condensed structural formula be C, CO, C, like that. So that it's very clear to tell that it's in the middle. So again, the whole compound would be considered a ketone, but the functional group would be a carbonyl. Carboxylic acids have a C double bond O, but they also have an OH attached. So because of that, we classify this as a whole different functional group. Instead of saying it's a carbonyl and a hydroxyl, the whole thing together is a carboxyl group. And when it's a part of a compound, the compound is a carboxylic acid. And that's because it does behave differently than either a carbonyl or a hydroxyl group on their own, so we need to classify it differently. Okay, so then esters have that C double bond O and an O. So we're starting off like a carboxylic acid, but then it has a carbon attached to the oxygen. So this is an ester. The whole compound would be considered an ester, whereas the functional group is just this part here. It is still considered a carboxyl group. The C double bond O, it makes that functional group carboxyl. The whole compound would be considered an ester. Amides have the C double bond O, but are also attached to a nitrogen. So the carbon could be attached to something else. The nitrogens could also be attached to something else. They could be hydrogens or they could be carbons. Doesn't matter. Hydrogen, they could be carbon. Doesn't really matter. But the important thing is that the nitrogen is attached to a carbon that also has a double bond O. And so this functional group, this part, is the amido group. And the whole compound then would be called an amide. Amines have nitrogen, so some kind of carbon with a nitrogen attached. The nitrogen could have hydrogens on it. They could have one hydrogen and some carbon group. It could have both of them be carbon groups. Doesn't matter, just as long as it's got that nitrogen on there, it's an amine. The whole compound would be considered an amine, and the functional group is an amino group. Now, halogenoalkanes. Halogenoalkanes have halogens attached to some carbon. So it would be carbon attached to fluorine, chlorine, bromine, or iodine. And they were typically named with a prefix instead. We'll get into naming more later, but I want you to recognize that this would be like a fluoroalkane. This would be a chloroalkane, a bromoalkane, or an iodoalkane. And it could be attached to just a single carbon or multiple carbons at any point in the chain. But that's going to have a halogen. And so you're going to name using those prefixes, fluoro, chloro, bromo, or iodo. So let's talk about arenes. Arenes have effectively a benzene ring that is attached to another chain of compounds, or another chain of carbons. So benzene, if you'll recall, has 6 carbon atoms in a ring, and each one of those has 1 hydrogen attached to it. Benzene also has 6 pi electrons. but because of the structure of benzene, all 6 of those are able to be delocalized. So they resonate, they move throughout the entire compound. So we represent that with a circle. So benzene, if I were to draw that as a skeletal structure, just looks like a hexagon with a circle in the middle. But what you can do is the benzene can serve as a functional group instead. So one of those hydrogens could be changed to a carbon and attached to other things like that. And so the overall compound would be considered an arene, and the functional group itself would be called a phenyl group. However, most of the time the names end in benzene, which is kind of funny. So instead of saying it's an arene, it's a benzene derivative. Just be able to recognize all of them. So let's look at a few examples. We've got this structural formula. We want to make it a skeletal formula. So we need to do just lines, basically. So we've got our first 2 carbons. The carbons are at the end of each, at the end of the line there. Then I have a C double bond C. So I'm going to represent that with 2 lines like that. And then I've got another C single bond C. Now you could have drawn it up or down. It does not give us enough information really here, and we have not talked about cis-trans isomers yet. So if they don't give you more information, we could do that either way. So those are our 4 carbons. Now we need to also include any of the functional groups. So we've got our halogen right there. So I'm going to show that chlorine. I'm also going to show an OH group on the last carbon. Everything else can be left. All of the other hydrogens are directly attached to carbon and can be assumed. So now we're going the other way. We want to take the skeletal equation, skeletal formula, and change it to condensed structural. I'm going to go ahead and do full and then condensed, just so you guys can see it, but you can jump straight to condensed if you're able. So in this one, I've got a carbon attached to chlorine, and there's another carbon. Remember, at the end of each line, there's another chlorine here, and then carbon, there's another carbon, and then this one has a bromine. But we're not done yet. We have to fill in the hydrogens. So carbon has to have 4 total bonds. That means this carbon needs another one and another one. And these carbons on the end need 3 hydrogens each to fill in. So this would be the complete structural formula. Now I'm going to write the condensed. So I'm going to go carbon by carbon. I have a CH3. I have a CHCl on the next one. I have a CHBr on the next one. And then I have a CH3 as the last group. And so that's our condensed structural. This one we're just taking the structural and going to condensed. So I want to go carbon by carbon. CH3 for the first carbon. The next carbon has an OH group. Some people will just write OH, some people will put it in parentheses. Either way is okay. But then it also has a CH3 group coming off of the carbon. That one does need parentheses. And then you'll see the CH3 on the end. And there's your condensed structural formula. Okay, so what is unique about carbon that enables it to form more compounds than the sum of all of the other elements' compounds? And that's because carbon has 4 valence electrons, and those 4 valence electrons are able to form 4 covalent bonds, which gives it immense versatility. It can form 4 single bonds, it can form double bonds, it can form triple bonds, and it can bind to many, many other atoms. And so that really, more than anything else about carbon, is what helps it make all of the different structures it can. Now, what are the advantages and disadvantages of different depictions of an organic compound? So structural formula, it shows everything, but it can take up a lot of space and it can be very time consuming, especially when you get into the really, really big molecules like biological molecules. A stereochemical formula shows the three-dimensional shape, like 3D space. But again, it can take up a lot of space and can be difficult to draw, especially when you have a very big molecule. A skeletal formula is nice in that it's quicker to draw, but it doesn't show every single atom, and it requires a little bit more knowledge to understand what's going on in a skeletal equation. Now, 3D models are interesting because you can see some of that 3D space. If you're using a computer simulation for those 3D models, you can manipulate them very quickly and easily, but they do require either more computing power or like a physical model, three-dimensional model. I'm going to add in here a molecular formula as another one. A molecular formula only shows the number and type of elements in the compound, which is nice and brief. However, it doesn't give us enough information to really understand what's going on in the structure. Now, this section also links to a higher level topic from 2.4 for up to amino acids. Amino acids have both an amine group and a carboxylic acid, like that. And if you have two of them, the OH can attract one of these H's from the amine group to form water, and that would be, I'll do it like this. It's going to form water as one of the products, but then it will attach, forming an amide bond, like this. And so this becomes a dipeptide. Oh, I missed a carbon in there. So this is a dipeptide because it has two amino acids stuck together using this amide linkage here. And because it has an amine group still on one end and a carboxylic acid group on the other, it can continue the chain and form a polypeptide, which we call protein. Now this section also links forward to reactivity, 3.2 and 3.4. Functional groups can be used to determine a reaction pathway between compounds, so like ethene into ethanoic acid. If we understand how double bonds react, then we could turn it into something that maybe has a particular functional group in it that could maybe be then turned into a functional group like a carboxylic acid. So by knowing all of the individual functional group reactions, we can choose from those to build up an overall reaction pathway.